Hello again, it's Dave Giles here for the next lesson of Cambridge International Education IGCSE Physics Unit P3 Waves. Today we are looking at sound. So our three learning objectives for today are to recall the range of human hearing, describe key terms loudness, pitch, amplitude, and frequency, and describe in detail how sound travels. Now, I've got some starter questions. I'll make them a little bit bigger so you can see them better. Okay, I'll give you a few seconds just to work your way through them, pause the video, and then I will talk you through how to answer them. Okay, so it's wave A, transverse or longitudinal, or rather is it representing transverse longitudinal wave? It's transverse. Near the circle part of wave A, that is a peak. Is wave B transverse or longitudinal? It is longitudinal. Near the circle part of wave B, that is a compression. And which of wave A or B could represent a sound wave? So a sound wave is longitudinal and B is definitely longitudinal. Although technically you could argue that you could use A to represent a sound wave. Okay. Okay, so a sound can be described as either high or low, and that is the pitch of the sound. So this thing is called an oscilloscope. And on an oscilloscope trace, the pitch of a sound is shown by how many waves there are, which is the frequency. The bigger the frequency, the higher the pitch. And the bigger the amplitude, the louder the sound. So amplitude is related to sound, bigger the amplitude, louder the sound, and frequency is related to pitch. Bigger the frequency, the higher the pitch. So very quick questions, one or the other. Largest amplitude, that is 1. Largest wavelength, that is 2. Loudest sound, it's the one with the biggest amplitude, so that is 1. The highest pitch, the highest frequency, so the most waves per second, so that would be 1. Okay, so match up the correct description of the wave here. So the first one, 2 seconds. Loud and low pitched is A. Loud and high pitched is C. Quiet and high pitched is D. And quiet and low pitched is B. So how well can we hear? So I'm going to use a website which will generate a tone. So you can hear the difference between something that is low pitched and something which is high pitched. So small frequency first. Pause it for 1 second. You should be able to hear that in the video. So that's something low pitched, a little bit higher. This doesn't sound very nice, I know. And you can keep increasing. You can hear the difference as you change the pitch. So I'm increasing the frequency. I'll stop that. And what I can do as well is use the other link here. You can try it yourself. You can open it. I can start a sound here and just listen up until you can no longer hear it. And I'm going to tell you when I stop hearing it. I can't hear it. Okay, so I stopped being able to hear it at about 14,000 hertz. However, the range of human hearing varies, but you can normally hear between 20 hertz and 20 kilohertz, which is 20,000 hertz. Now, as you get older, your range of hearing decreases. So I am almost 40. So I got up to about 14,000 hertz. Now, if you're an IGCSE student, you're probably about 25 years younger than me. So the chances are you could hear a higher frequency than I did there. So when something vibrates, it causes the particles around it to vibrate. When one particle collides with another particle, it transfers the energy and the sound wave. This is how sound travels here. So you see something vibrating, it's causing the air particles to move backwards and forwards. And although it looks like the particles moving all the way from here to there, if you look at one particle and just focus on this one particle, you notice each particle only moves a fairly short distance. However, the energy is still transferred from here to there. Okay, and you can also see that in a speaker here. So the way a speaker works is it takes a signal, which is a digital signal or analog signal, and it converts it from an electrical one to a sound one. So it'll have an electromagnet in here, which acts a bit like the human, which acts a little bit like your voice, and the magnet causes this to vibrate and release sound at a certain frequency, which we hear as music. So which of these mediums can sound travel? Well, it can actually travel through all three, solid, liquid, and gas. As long as there are particles present, then sound will be transmitted. The closer together the particles are, the faster the sound will travel. So in air, sound travels at around 330 meters to 350 meters per second, depending on a few factors such as temperature and pressure. So, quick question, you can have a go at this yourself and pause it. In which medium, solid, liquid, or gas, do you think sound would travel faster? Explain your answer. Well, the answer is a solid. More particles in the same space, i.e. it's denser, so the particles are closer together. So easier for the particles to vibrate and pass on the energy to the next particle. So actually sound, air, which is where we are now, you listen to me unless you've got your laptop on underwater. Sound is traveling about 330 to 350 meters per second. But if you were listening underwater, it would actually be traveling faster to your ears. So there was a film back in 1979, before even I was born. A great film. It's called Alien, and the tagline for it is, "In space, no one can hear you scream." Now, I'm going to actually point out there's actually some truth. It's fully true, that statement, because in space, there are no particles. Space is a vacuum. So in space, sound does not travel due to the lack of particles. Okay, and you also need to be able to calculate the speed of sound. So there's various ways to do it. The most common one is you'll have two people. You can also do it with one person, although it's a little bit trickier. They might clap their hands or clap two pieces of wood together, and you're a certain distance from the wall. You wait for it to hit the wall and wait till you hear it again. Now, with human reaction time being about a quarter to half a second, the total distance this travels is 100 meters there and 100 meters back, so 200 meters. You're going to get quite a bit of error there because that should take less than a second due to traveling at 330 meters per second to get there and back. So normally what you do is you set up a beat. Now, I'm not particularly musical, so I'm not great at this. When the sound wave, when you start clapping, you create a sound wave, hits the wall. When you hear the echo, the reflection back in your ear, you hit it again, and so on and so on. You do this 10 times and then stop the timer there. You do the total distance, so say the total time. So if we said for argument's sake, it took 30 seconds to get 10 oscillations. So you can hear it 10 times. So in that time, it has traveled 100 meters there, 10 times, and 100 meters back 10 times. So that is a total distance traveled of 2,000 meters. I said it took 30 seconds. So it'll be 1,000 divided by 30, which gives you actually 33.3. So my time was a little bit out there. I should have taken a different time to that. Anyway, here's a quick some questions that I made up myself for you to have a go at, which summarize what we've done so far. So when two friends are standing on a beach, when they shout, they can hear themselves 0.6 seconds later. Explain as fully as you can why this happens. Sound reflects off the cliff, comes back the way it came from. And given that they are 100 meters away from the cliff, calculate the speed of sound. The total distance is 200 meters, because I'll travel there and back. Speed is distance over time. 200 divided by 0.6, 333 meters per second. And the range of human hearing is 20 hertz to 20 kilohertz, or 20,000 hertz. Which three of the diagrams below show traces with the same loudness? So it's the ones with the same amplitude, so that would be A, C, and D. Which two show traces of the same frequency? So the same number of waves present, that would be D and E. There is no air in space. Astronauts in space cannot hear sound from outside their spacesuits. Explain why. Sound can't travel through a vacuum because there are no particles for vibrations. Okay. So now we'll have a quick look at some paper 2 multiple choice questions. Which of the following does not produce a sound wave? A bell ringing underwater, a gun fired in a room with no echoes, a hammer hitting a block of rubber, an explosion in outer space. So it's the place with no particles, that is outer space, D. The frequency of a musical note is increased. The student hearing the sound detects an increase in which property? So the sound, that is the pitch, because that is related to frequency. In which situation do sound waves not travel? So we know it's where there's no space, so from a satellite in space to Earth. Okay, so it's a calculation. An experiment and measure the speed of sound. The student uses a stopwatch to find the time taken for a sound wave to travel from X to Y. She does this 6 times. For which value of the time should be used to calculate the speed of sound? For this one, actually, it's not even really related to what we've covered today. This is just taking a mean. So the mean of these values, so let's quickly add them up. Get 0.5 plus 0.7 plus 0.6 plus 0.4 plus 0.9 plus 0.5, which gives you 3.6 divided by 6 gives you 0.6 seconds. Which row correctly compares the speed of sound in air, liquid, and solid? So the speed is fastest in solids, then liquids, then air, so the answer is D. A tennis player hits a ball hard 0.4 seconds later, he hears an echo from the wall. The speed of sound in air is 330 meters per second. How far away is the player from the wall? Different ways that you can do this, but I'm going to half this straight away just to make it easy. So it takes 0.4 seconds to travel there and back. So it takes 0.2 seconds to travel to the wall. So speed is distance divided by time. Distance is speed times time. So it's 330 times 0.2, which is 66 meters. And the range of audible frequency for elephants is 10 hertz to 12,000 hertz, and for horses, 55 hertz to 33,000 hertz. Which statement about the range of audible frequencies for a healthy human ear is correct. And we've got a few statements. So the first one, the human ear can hear all the sounds heard by both elephants and horses. That's not true because it can't hear the low frequencies for elephants or the high frequency for horses. The human ear can hear all sounds heard by elephants. Straight away, that's not true because we just said I can't hear the low frequencies of elephants. The human ear can hear all sound heard by horses. Again, not true because it can't hear the high ones. The human ear cannot hear all the sounds heard by an elephant, nor those heard by horses. That is true. So it's D. And very similar to the question I gave you a few ago, but this time it's got values in. So speed of sound, now we know in air it's about 330 to 350, so we'll say 340. So it must be one of these two. It's going to be fastest in solid, which is iron, and water will be the middle one, so therefore the answer is A. And an observer stands at the finish line of a 100-meter race. He wants to time the winner's run. He starts his stopwatch as soon as he sees the smoke rather than starting the gun instead of when he hears the bang. Why does he do this? And it's simply because light travels much faster than sound. Okay, so the next lesson, which I'll be uploading soon, is on ultrasound. I'll post a link down below. Thank you very much, everyone, and I'll see you for the next lesson.